Today we define the minimal polynomial and briefly preview rational canonical form. Briefly is the important word. We are not turning this linear algebra course into an abstract algebra dungeon. At least not today. Jordan form gave us a powerful way to understand complex operators using eigenvalues and Jordan blocks. The minimal polynomial measures how much polynomial force is needed to make an operator become zero. Rational canonical form goes further. It gives a normal form over any field, even when the polynomial refuses to split nicely. Polynomials, naturally, have chosen violence. First, a non-zero polynomial that kills t always exists in finite dimension. The space of linear operators has dimension n squared, so the list I, t, t squared, and so on must eventually become linearly dependent. That dependence gives a non-zero polynomial p with p of t equal to 0. Even operators eventually run into a wall. Inspirational. In a bleak way. Among all non-zero polynomials that kill t, choose one of smallest degree and scale it so the leading coefficient is 1. That polynomial is called the minimal polynomial of t. It is minimal because it has the smallest degree, not because it has a minimalist lifestyle brand. Sadly, notation has no taste. The minimal polynomial divides every polynomial that kills t. Use polynomial division. Write p as q times the minimal polynomial plus a remainder r of smaller degree. Substitute t. The first term vanishes, so r of t is 0. Minimality forces r to be 0. Because Cayley-Hamilton says the characteristic polynomial kills t, the minimal polynomial divides the characteristic polynomial. So the characteristic polynomial counts algebraic multiplicity, while the minimal polynomial records the largest obstruction to diagonal behavior. That sentence is doing a lot of work. Unlike most committee statements, it is actually useful. Over the complex numbers, Jordan form makes the minimal polynomial extremely readable. For each eigenvalue lambda j, look at the largest Jordan block size for that eigenvalue. Call it Sj. Then the minimal polynomial is the product of z minus lambda j to the Sj. So the minimal polynomial does not count every block. It only cares about the worst block for each eigenvalue. Harsh, but efficient. Consider the matrix A from the matrix exponential example. Its characteristic polynomial is z-1 squared times z-2. The eigenvalue 1 has a Jordan block of size 2, while the eigenvalue 2 has block size 1. Therefore the minimal polynomial is z-1 squared times z-2. If the 1 block had split into two separate 1 by 1 blocks, the exponent would drop to 1. The polynomial is watching the nilpotent part like a tired supervisor. This also gives a clean diagonalizability test over the complex numbers. An operator is diagonalizable exactly when its minimal polynomial has no repeated roots. Repeated roots mean a non-trivial Jordan block is lurking nearby, probably pretending to be innocent. Jordan form relies on factoring polynomials into linear factors. Over a general field, that may fail. Even over the real numbers, x squared plus 1 refuses to split. So rational canonical form asks for a normal form that works without begging the field to contain all roots. Fields, naturally, are not known for customer service. Rational canonical form replaces Jordan blocks with companion matrices built directly from polynomials. It works over any field and does not require eigenvalues to exist inside that field. That is the trade. Less geometric intuition. More algebraic reliability. A very on-brand bargain for mathematics. Given a monic polynomial Q, its companion matrix stores the coefficients of Q in one structured block. The exact layout depends on convention, because apparently even matrices enjoy regional dialects. The important point is that the block is built from Q itself, not from roots of Q. Rational canonical form says that a matrix is similar to a block diagonal matrix made of companion matrices. The polynomials Q1 through Qr can be chosen so that Q1 divides Q2. Q2 divides Q3. And so on. The last polynomial is the minimal polynomial. And the product of all of them is the characteristic polynomial. Here is the abstract algebra viewpoint in 1 minute. Let f bracket x act on V by saying that x times V means TV. Then P of x times V means P of t applied to V. So V becomes an f bracket x module. The real engine is the structure theorem for finitely generated modules over a PID. Since f bracket x is a PID, that theorem gives the invariant factors. And the invariant factors give rational canonical form. That is why this topic is usually treated seriously in abstract algebra. Linear algebra can introduce the result. But the proof lives in module theory. Behind a door labeled "Bring snacks." So the minimal polynomial is the smallest monic polynomial that kills the operator. And it divides every other polynomial that kills the operator. Over the complex numbers, Jordan form makes it easy to read from the largest block sizes. Rational canonical form is the field-independent version, built from companion matrices and explained most naturally by modules over f bracket x. For this linear algebra series, that is enough. We wave at the abstract algebra machinery, acknowledge it is powerful, and wisely do not move in with it.